Good day. My name is Ahmet Selim Ayaz. I'm a physics major in Bilkent University. Today, I will present the experimental work I conducted for the Phys 102 course. In the study, I experimentally determined the vacuum permittivity using a parallel plate capacitor and vacuum permeability mu naught using a solenoid. Subsequently, I combined these measurements to calculate the speed of light, utilizing the theoretical relationship between these two fundamental constants. This experiment serves as a practical demonstration of how electromagnetic properties of free space are interrelated and how fundamental constants can be measured indirectly through careful analysis. It also highlights the significance of experimental accuracy and error management in determining physical quantities.
In the first part of the experiment, I employed a parallel plate capacitor. The capacitance C of an ideal parallel plate capacitor is theoretically given by the expression C equals epsilon naught times A over D, where A is the area of the plates and D is the separation between them. To determine epsilon naught, I measured the capacitance for varying plate separations and plotted the capacitance values against 1 over D. According to the theoretical relationship, the resulting graph should be linear with a slope equal to epsilon naught times A. Since the plate area A is known, I was able to isolate and calculate epsilon naught from the slope. Here is the setup that I used for the first part of the experiment. We constructed parallel plate capacitor using two square metal plates, and then we measured the capacitance with a multimeter while increasing the distance between the plates in multiples of 2 mm. Then finally we discharged the stored charge through a resistor after each measurement to ensure the reliability of the data. In the second part of the experiment, I utilized a solenoid to measure the vacuum permeability mu naught. The magnetic field B inside an ideal solenoid is given by B equals mu naught times N times I, where N is the number of turns per unit length and I is the current through the solenoid. Since measurements were taken near the ends of the solenoid, the effective magnetic field is approximately half of the central value. Taking this factor into account, I measured the magnetic field for different current values and plotted B versus I. The slope of this graph yields mu naught times N. Given that N was known to be 1778 turns per meter, I calculated mu naught accordingly. And here is the setup that I used for the second part of the experiment. We constructed the solenoid by wrapping a thin copper wire around a PVC pipe, ensuring that the length of the pipe was much greater than its diameter. We positioned a Hall probe near one end of the solenoid to take measurements and kept it securely in place. To eliminate the influence of Earth's magnetic field on our readings, we adjusted the zero control on digital Gauss Teslameter until the LCD screen displayed a zero reading. We then used a variable DC power supply to pass an electric current through the solenoid, gradually increasing the current while measuring the magnetic field at each step of the process. We plotted the collected data and examined the resulting trends. We then applied the previously outlined procedures to calculate the values of epsilon naught and mu naught. We substitute these values into the formula square root of 1 over epsilon naught times mu naught to obtain the experimental value of the speed of light. Of course, some discrepancies arose due to equipment limitations and human errors, which we discuss in more detail in the report. Finally, we obtained the speed of light as 3 times 10 to the 8 meters per second. Thank you for your attention.